There are marine fossils at the summit of Everest. At 8,888 meters of altitude, in the highest rock on Earth, there are shells of creatures that lived at the bottom of a tropical ocean 150 million years ago. They did not arrive there through any accident. They were not carried by wind or launched by any volcanic eruption. They are there because the rock that today forms the summit of Everest was at that time the sediment at the bottom of a warm, shallow sea that covered much of what is today Central Asia, a sea that geologists call the Tethys. The history of the Tethys also connects to the daily lives of billions of people in ways they rarely think about. The petroleum that heats homes, drives cars, and generates electricity in much of the world came from organisms that lived in the Tethys. The marble and limestone in buildings across Europe and the Middle East are Tethys seafloor sediments. The mountains that define the landscape of a vast swathe of the planet from Spain to China are the product of the Tethys closure. And the monsoon that provides rain for 2 billion people in South and East Asia exists because the Himalaya exists, and the Himalaya exists because the Tethys is gone. The story of the Tethys is also a story about the patience of evidence. The shells at the summit of Everest waited 150 million years to be found. The oil fields of Arabia stored their energy for the same duration. Evidence does not expire. It simply waits, embedded in rock or fossil or sediment, until a species capable of reading it finally arrives. We are that species, and we have barely begun to read what the Earth has kept for us. The scale of the Tethys also helps calibrate our sense of what is permanent and what is temporary. The Sahara Desert is approximately 5,000 years old in its current form. The Roman Empire lasted approximately 500 years. The Tethys lasted 200 million. Everything that humans call ancient is geologically recent. The Tethys puts all of it in proportion. When we fall asleep tonight, that sleep is possible because the Earth maintained conditions stable enough for complex life over hundreds of millions of years. The Tethys was part of that stability, regulating climate and carbon across the Mesozoic. The world that allowed us to evolve and to build civilization was shaped, in ways we are still discovering, by an ocean that no human being ever saw. Understanding the Tethys is understanding the world we live in. The geography we take as given, the energy systems we depend on, the climate patterns that organize agriculture across vast regions. All of it traces back to an ocean that no human being ever saw, that existed and died long before our species existed. That is the remarkable thing about deep time. The past does not stay in the past. It shapes the present in ways that are invisible until someone teaches you to look for them. Contemplating the Tethys also gives a different perspective on the urgency of the present moment. The forces that closed that ocean were unstoppable and operated on timescales of millions of years. The forces we are now adding to the Earth system through greenhouse gas emissions operate on timescales of decades and centuries, but they are changing the planet in ways that will outlast our civilization by millions of years. In that sense, we are becoming a geological force comparable in its effects, if not in its duration, to the tectonic forces that killed the Tethys. The Tethys was the largest ocean that has existed in the last 200 million years of the Earth's history. At its maximum extent, approximately 150 million years ago, it covered an area comparable to all current oceans combined. It was a tropical sea, warm, shallow at its margins and deep at its center, with coral reefs extending for thousands of kilometers and a marine biodiversity that rivaled the best reefs of the modern world. And it was situated approximately where today we find Europe, the Mediterranean, the Middle East, Central Asia, and the Himalaya. It no longer exists. It disappeared when the continents surrounding it began to move toward each other, slowly closing it like the jaws of a gigantic press, until what had been an ocean became a mountain range. The Alps, the Caucasus, the Zagros, the Hindu Kush, the Karakoram, and the Himalaya are all the wrinkles produced by that continental closure. The Mediterranean, the Black Sea, the Caspian Sea, and the Aral Sea are the last remnants of that lost ocean, isolated puddles of the sea that once was. If you are enjoying this channel and want to keep exploring the worlds that the Earth has lost, subscribe now. There are many more stories like this one waiting for you. Tonight we explore the history of the Tethys. How it was born, how it lived for 200 million years, how it died beneath the colliding continents, and what it left behind when it disappeared. It is a story written in the highest mountains in the world, in the fossils of the animals that lived in its waters, and in the geography of the planet we inhabit today. The story of the Tethys also teaches us something about humility. For centuries, naturalists who found marine shells high in mountain ranges did not understand what they were seeing. They proposed explanations that today seem naive, because they lacked the conceptual framework needed to correctly interpret the evidence. Only when science developed the theory of plate tectonics did those mountain fossils find their correct explanation. They had not climbed to the Himalaya. The Himalaya had grown around them. To understand the Tethys, one must go back to the world of 250 million years ago, when all current continents were united in a single supercontinent called Pangea. Pangea was an enormous continent, so large that its interior was thousands of kilometers from any coast and received barely any rain, while its coasts were exposed to a single gigantic ocean, the Panthalassa, that covered the rest of the planet. It was a world different from the current one in many respects, warmer on average, with less temperature difference between the poles and the equator, with climate patterns dominated by the most intense seasonal monsoons the Earth has ever had. The world of Pangea, from which the Tethys was born, was also a world of a very different terrestrial fauna from the current one. The first dinosaurs appeared precisely in the period when the Tethys was beginning to open, approximately 230 million years ago. During most of the history of the Tethys, dinosaurs dominated the land while the great Tethys reptiles dominated the seas. When the Chicxulub asteroid eliminated the non-avian dinosaurs 66 million years ago, the Tethys still existed, though already much reduced. The mammals that survived that extinction and eventually gave rise to humans began their diversification in a world in which the Tethys was still a considerable sea. The opening of the Tethys also produced the first major separation of terrestrial faunas between the northern and southern landmasses. As Eurasia and Gondwana separated and the Tethys widened between them, the animals on each landmass began evolving in isolation. That separation is reflected in the deep evolutionary differences between the mammalian faunas of the northern and southern continents today. The marsupials of Australia and South America, the lemurs of Madagascar, and the unique mammals of Africa all reflect evolutionary paths that diverged when the Tethys separated Gondwana from Eurasia. The coral reefs of the Tethys were also extraordinary in their diversity and geographic extent. At their maximum development in the Jurassic, Tethys reefs stretched from what is now Central America to what is now Southeast Asia in a nearly continuous belt of shallow water carbonate productivity. That belt of ancient reef limestone, now folded into mountains or buried beneath younger sediments, represents the accumulated skeletal material of trillions of organisms across tens of millions of years. The Tethys also had a profound influence on the distribution of water vapor in the ancient atmosphere. A tropical ocean of that size, covering a vast equatorial belt, would have been an enormous source of evaporation, pumping water vapor into the atmosphere at rates that affected precipitation patterns globally. The loss of that equatorial moisture source as the Tethys closed contributed to the drying of the continental interiors that is one of the defining climate trends of the Cenozoic. The rifting that opened the Tethys also produced enormous outpourings of flood basalt lava in what are now Siberia and other parts of the northern landmass. Those volcanic episodes, among the largest in Earth history, released enormous quantities of carbon dioxide into the atmosphere, contributing to the warm greenhouse climate of the Triassic and Jurassic that made the Tethys such a productive tropical sea. The position of the Tethys, between approximately 30 degrees north and 30 degrees south, placed it in the tropical zone of the planet, where solar radiation is most intense and water temperatures are highest. Those conditions favored the extraordinary biological productivity that characterized the Tethys throughout its history. Coral reefs, large mollusk populations, fish of all types, and the great marine reptiles that dominated the Mesozoic seas. The Tethys was for most of its history the most productive ocean on the planet, the center of marine life in the Mesozoic world. The volcanic activity associated with the subduction of the Tethys was also an important component of the history of that ocean. When the oceanic crust sinks under the continental crust, the heat and pressure release fluids from the hydrated minerals of the oceanic crust, and those fluids rise toward the overlying mantle, lowering its melting point and producing magma. That magma rises toward the surface and produces volcanoes, many of which were volcanic islands in the Tethys or volcanoes on the continental margins. The volcanism of the Alps and many other regions of the ancient Tethys is documented in the volcanic rocks surviving in those mountains. In that world of Pangea, the Tethys did not yet exist as a separate ocean. It existed as a wide gulf or bay opening from the Panthalassa toward the interior of Pangea from the east, a sort of sea wedge penetrating between the northern and southern continental masses. The history of the Tethys truly began approximately 220 million years ago, when Pangea started to fracture. The first fracture separated the northern continental mass, which geologists call Eurasia and which included what are today North America, Europe, and Asia, from the southern continental mass, Gondwana, which included what are today South America, Africa, Antarctica, Australia, and India. Between those two separating continental masses, the sea that had previously been a gulf began to widen and become a proper ocean. That new ocean, the Mesozoic Tethys, grew for tens of millions of years as Laurasia and Gondwana moved apart from each other. At its maximum development, between 150 and 100 million years ago, the Tethys was a tropical ocean of warm waters extending from what is today Central America in the west to what is today Southeast Asia in the east, crossing what is today Southern Europe, North Africa, the Middle East, and South Asia from west to east. The movement of the continents from Pangea to the current configuration was not a uniform process but a series of discrete tectonic events occurring at different times and places. North America and Europe separated approximately 180 million years ago, opening the North Atlantic. South America and Africa separated approximately 140 million years ago, opening the South Atlantic. Australia and India separated from Antarctica between 80 and 100 million years ago. And India, separated from Africa approximately 130 million years ago, began its long northward journey that would eventually lead it to collide with Eurasia and close the eastern Tethys. The velocity at which India traveled northward to collide with Eurasia is extraordinary by plate tectonic standards. Current estimates suggest India moved northward at speeds of up to 20 centimeters per year in some periods, approximately double the typical speed of plate movement. That anomalous speed is the subject of active research. Geologists are trying to understand what mechanisms produced such rapid movement, and current hypotheses include the particularly efficient subduction of the Tethys oceanic crust and the presence of a mantle heat plume beneath the Indian plate that may have contributed to accelerating its movement. Life in the Tethys was extraordinary. During the 200 million years that ocean lasted, its waters were the setting for some of the most spectacular marine faunas that have ever existed in the history of the Earth. Ichthyosaurs were perhaps the most abundant and most adapted of the great reptiles that dominated the Tethys waters during the Triassic and Jurassic. With their dolphin shape, enormous eyes adapted for seeing in deep water, and fins allowing them to swim with an agility comparable to that of modern cetaceans, ichthyosaurs were top predators that hunted fish, mollusks, and other marine animals with great efficiency. Some genera reached lengths of 15 or 20 meters, comparable to those of the largest current whales. The Tethys reef systems deserve particular attention for what they reveal about the evolution of reef-building life on Earth. The Triassic period, immediately following the greatest mass extinction in Earth history at the end of the Permian, saw the Tethys recovering its reef ecosystems from near-zero diversity. The speed of that recovery, which paleontologists can trace in the Tethys sedimentary record, provides some of the best data we have on how marine ecosystems rebuild after catastrophic events. That data is directly relevant to understanding the resilience of modern coral reefs in the face of the current climate change-driven bleaching events. The Tethys seafloor sediments also contain a remarkable record of ancient ocean chemistry. The ratio of different carbon isotopes preserved in carbonate fossils reflects the productivity of the ocean at the time those fossils formed. Reading those isotopic signals across millions of years of Tethys history reveals cycles of productivity change that correlate with the major geological and biological events of the Mesozoic, connecting ocean chemistry to the evolution of life in ways that researchers are still working to fully understand. The largest known ammonite ever found, Pangea sepenredensis, had a shell diameter of approximately 1.8 meters when complete. That animal, which must have been one of the most impressive creatures of its era, lived in the final few million years before the Chicxulub impact ended the Ammonites forever. That combination of extraordinary size and imminent extinction makes it one of the most poignant figures in the entire fossil record of the Tethys. The extinction of the rudists at the end of the Cretaceous, 66 million years ago, left a gap in the reef-building ecosystem that was eventually filled by the expansion of modern scleractinian corals. That transition, from a rudist-dominated reef world to a coral-dominated reef world, represents one of the most profound changes in the structure of shallow marine ecosystems in the last 100 million years, and understanding it requires understanding the Tethys in which both the rudists and the early scleractinians evolved. The giant ammonite Pangea sepenredensis, discovered in Westphalia in Germany in rocks that were the bottom of a Tethys-connected sea in the Cretaceous, had a shell diameter of approximately 1.8 meters when complete. That animal, which must have been one of the most impressive creatures of its era, was also one of the last of its lineage. It lived in the final few million years before the Chicxulub impact ended the Ammonites forever. That combination of extraordinary size and imminent extinction makes it one of the most poignant figures in the entire fossil record of the Tethys. The diversity of ammonite shell shapes, from tightly coiled to loosely coiled to straight to exotic corkscrew forms, reflects not just aesthetic variety but functional diversity. Different shell shapes were adaptations to different ecological niches and different behaviors. Tightly coiled forms were probably fast swimmers in open water, while loosely coiled forms may have been slower-moving bottom dwellers. That ecological diversity within a single group of organisms speaks to the extraordinary variety of habitats and opportunities available in the Tethys at its height. The corals of the Tethys also deserve special attention. The reefs of the Mesozoic Ocean were not built by the same types of corals that build modern reefs. Scleractinians, the coral group that builds modern reefs, appeared in the Triassic and diversified in the Tethys waters during the Jurassic and Cretaceous, but in the Tethys also lived the rudists, those reef-building mollusks mentioned earlier, and several other groups of organisms that built reef structures in ways that have no equivalent in current oceans. That diversity of reef-building mechanisms in the Tethys reflects the extraordinary productivity of that ocean and the intensity of competition for resources in its shallow waters. The extinctions of the Tethys megafauna at the end of the Cretaceous, 66 million years ago, also tell a story about the vulnerability of the most specialized groups to extreme disturbances. Ammonites were organisms that had evolved for 180 million years to live in the specific conditions of the Tethys seas and their successors. When the Chicxulub asteroid darkened the sun for years and cooled the oceans, the conditions that had made their extraordinary diversity possible disappeared suddenly. The less specialized groups, those that could survive under more variable conditions, survived. The Ammonites, too well adapted to a world that no longer existed, did not. Plesiosaurians added another dimension to predation in the Tethys. With their long necks and 4 powerful fins, they were slower swimmers than Ichthyosaurs but perhaps more versatile, capable of turning quickly to catch prey in shallow waters or diving to considerable depths in search of cephalopods. The mosasaurs arrived later, in the Cretaceous, But when they arrived, they rapidly became the dominant predators of the late Tethys seas. With their long bodies and jaws capable of opening at impossible angles to crush the shells of ammonites and other mollusks, mosasaurs were the Mesozoic equivalents of modern orcas, apex predators that could eat practically anything they encountered. But the true protagonists of the Tethys, in terms of diversity and abundance, were the invertebrates. Ammonites, those cephalopods with spiral shells that are the most recognizable fossils of the Mesozoic, reached extraordinary diversity in the Tethys waters. More than 10,000 species of ammonites have been described from Tethys sediments, with shells of shapes and sizes ranging from a centimeter to 2 meters in diameter. That diversity of forms reflects the extraordinary diversity of ecological niches available in such an extensive and productive tropical ocean. The death of the Tethys was one of the slowest and most monumental geological transformations in the history of the Earth. It did not happen suddenly, nor did it have a single cause. It was the result of hundreds of millions of years of continental movement that eventually closed the ocean from all sides. The sediment record of the Tethys closure preserved in the deltas of the great South Asian rivers is one of the most complete geological archives available anywhere on Earth. The Bengal fan, the submarine delta deposited by the Ganges-Brahmaputra river system at the bottom of the Bay of Bengal, is the largest submarine fan on Earth, with sediment thicknesses exceeding 20 kilometers in its proximal parts. That enormous accumulation of sediment represents 50 million years of Himalayan erosion, with each layer recording the composition of the rocks being eroded in the mountains at the time of deposition. Reading the composition of those sediment layers from bottom to top is like reading a record of the Himalayan uplift in reverse chronological order, from the first collision of India with Eurasia to the present day. The geological maps of the regions surrounding the ancient Tethys are among the most complex on Earth, reflecting the enormous tectonic complexity that the Tethys closure produced. A geological map of Turkey shows dozens of distinct terrains, fragments of continental and oceanic crust assembled by the various phases of Tethys subduction and continental collision. Each terrain has its own geological history, its own fossils, and its own sequence of rock types, and understanding how they fit together is like solving a puzzle whose pieces were scattered across thousands of kilometers of ocean before being jumbled together by plate tectonics. The oldest ocean floor on Earth today is about 200 million years old, found in the western Pacific. The Tethys oceanic crust that was subducted during the Himalayan collision was consumed completely, leaving no trace of the original ocean floor. Its existence is known only from indirect evidence: the ophiolites, the fossils of its sedimentary cover, and the geochemical signatures preserved in the rocks of the mountains that grew where it sank. The paleomagnetic record of the Tethys closure is also extraordinarily detailed. The magnetic minerals in volcanic rocks produced at the spreading ridges and subduction zones of the Tethys recorded the direction of the magnetic field at the time of their formation, and those records can be read today to reconstruct the position and orientation of the tectonic plates involved in the Tethys closure with great precision. That paleomagnetic record is one of the primary datasets used to reconstruct the geography of the Tethys at different times in its history. The discovery that the rocks at the top of Everest are limestone formed in the Tethys was made in the 1920s by geologists accompanying the first British expeditions attempting to climb the mountain. Those geologists, who were not climbers themselves but scientific observers, recognized the marine fossils in the high-altitude rocks and correctly identified their origin as seafloor sediments. Their finding was one of the first confirmations from field observation of the theory that the Himalayas had risen from a former ocean floor. The carbon cycling implications of that erosion are also significant. The Himalayan limestones being eroded contain carbon that was fixed by Tethys organisms millions of years ago. As those limestones erode, the carbon they contain is carried by rivers to the ocean, where it is eventually deposited and removed from the atmosphere. That process has been removing carbon dioxide from the atmosphere for the last 50 million years, contributing to the long-term cooling trend that led from the warm Eocene to the ice ages of the Pleistocene. The death of the Tethys, through the mountains it raised and the carbon those mountains sequester as they erode, may have been one of the factors that eventually made the Earth cold enough for human beings to evolve. The hazard implications of the Himalayan geology are also practically important. The Himalayan glaciers, threatened by climate change, are one of the main natural hazards of the region. Glacial lake outburst floods, known as GLOFs, occur when a glacial lake fails suddenly, sending a wall of water and debris down into the river valleys below. As warming causes glaciers to retreat and glacial lakes to grow larger, the risk of GLOFs is increasing across the entire Himalayan range, with serious implications for the hundreds of millions of people living in the river valleys downstream. The fundamental mechanism was subduction. When two tectonic plates meet and one of them is oceanic, the oceanic plate, which is denser than continental crust, sinks under the continental plate in a process called subduction. That sinking plate drags with it the oceanic crust and everything on it, including the sediments accumulated at the seafloor over millions of years. And as the oceanic plate sinks, the ocean above it shrinks, as if someone were pulling the tablecloth of a table from below. That is exactly what happened with the Tethys. As Gondwana began to fragment between 130 and 100 million years ago, the pieces composing it began to move northward, toward Eurasia. India, which had been part of Gondwana, separated from Africa and began its long northward journey. The Tethys oceanic plate between India and Eurasia began to subduct under Eurasia, being consumed as India advanced. The subduction of the Tethys oceanic crust under Eurasia was not a uniform process but a sequence of events that geologists can reconstruct from the rocks that subduction left behind. The ophiolites, those fragments of oceanic crust that remained adhered to the continental margins rather than sinking completely, are distributed throughout the entire mountain system surrounding the ancient Tethys, from the Alps to the Himalaya, and each ophiolite is a fragment of the puzzle that geologists use to reconstruct the history of the Tethys closure. The high-pressure metamorphic rocks found in the subduction zones of the ancient Tethys also preserve information about the conditions that existed at that zone where oceanic crust sinks beneath continental crust. Those rocks, produced at pressures and temperatures that only exist at tens of kilometers depth, contain minerals stable only under those extreme conditions, and their presence at the surface is proof that at some moment they were buried at great depth before being exhumed by erosion and subsequent tectonic movements. They are literally rocks from the Earth's interior brought to the surface by the story of the Tethys. The collision of India with Eurasia, which began approximately 55 million years ago and continues to this day, is the most important tectonic event of the last 100 million years. When two continental masses collide, neither sinks under the other, because continental crust is too light to subduct. Instead, the two continental masses are compressed and folded, accumulating the material that was between them in a mountain range that grows in height as the collision continues. That is the reason why the Himalaya is the highest mountain range in the world, because India continues pushing against Eurasia, and the Himalaya continues growing at a rate of several millimeters per year. The history of the Tethys death is not only the history of the Himalaya. While India was closing the eastern Tethys from the south, other fragments of Gondwana were doing the same from the southwest. Africa began moving northward approximately 100 million years ago, approaching Europe. That movement was slowly consuming the western Tethys, and approximately 40 million years ago Africa and Europe began to collide in what is today southern Europe. That collision produced the Alps and the Pyrenees, the mountain ranges that today separate Mediterranean Europe from Central Europe. The biological connection between the Mediterranean and the Caspian Sea, separated by thousands of kilometers of continental land today, is one of the most striking living proofs of their shared Tethys ancestry. Species of sturgeon, eels, turtles, and other animals that exist in both seas and that could not have traveled from one to the other by any current route are living testimony that those two water bodies were connected in the geologically recent past. The Caspian sturgeon, whose caviar is among the most expensive foods in the world, is the biological heir of fish populations that once swam through the connected waters of the ancient Tethys. The ancient coastlines of the Tethys are also preserved in the geological record in the form of ancient beach deposits, coastal lagoon sediments, and remains of coastal ecosystems. Those ancient coastlines, now exposed in mountain gorge walls or quarry faces, provide snapshots of what the margins of the Tethys looked like at specific moments in its history. Some contain footprints of the dinosaurs that walked along the Tethys shores, preserved in hardened mud of ancient tidal flats, a direct physical connection between the two great dynasties of the Mesozoic world. The biogeographic connections between the Mediterranean and the Black Sea are a direct consequence of Tethys history. The Black Sea, now an almost completely isolated basin with anoxic deep waters, was connected to the Mediterranean until very recently in geological terms. The species that exist in both seas reflect that shared history, and the evolutionary divergence between Mediterranean and Black Sea populations of the same species can be used to date the timing of the final separation of the two basins. The warm shallow waters of the Tethys margins, where sunlight could penetrate to the seafloor and sustain photosynthesis, were also the setting for the evolution of many of the animal groups that today dominate marine shallow water environments. Echinoids, sea stars, crabs, shrimp, and the modern families of bivalves and gastropods all diversified dramatically in the Tethys during the Mesozoic, exploiting the enormous variety of habitats available in that tropical shallow water world. The geological evidence for the timing of the separation of the Mediterranean and Caspian basins comes from multiple sources, including the fossils of organisms that existed in both basins when they were still connected and that then diverged evolutionarily after the connection was severed. Those fossils, found in the sediments of the late Miocene and early Pliocene, provide a biological clock that confirms the timing of the final separation of the two basins, which occurred as the tectonic closure of the Tethys in the region of the Caucasus was completed. The future of the Mediterranean as a basin is also geologically predictable in broad outline. Africa continues moving northward at approximately 2 centimeters per year. The Strait of Gibraltar continues closing slowly. The Adriatic Sea, the narrowing arm of the Mediterranean between Italy and the Balkans, is in the early stages of becoming a new collision zone as the Adriatic plate continues to push northward. In tens of millions of years, the geography of the Mediterranean region will be as unrecognizable to us as the Tethys geography would be to the Romans whose civilization was built on its remnant shores. Arabia, which at that time was still part of Africa, also began separating from the African continent approximately 35 million years ago, opening the Red Sea and the Gulf of Aden. But at the same time, Arabia was approaching Eurasia from the south, and approximately 20 million years ago it collided with Iran, producing the Zagros Mountains and closing another section of the ancient Tethys. That Tethys closure in the region of what is today the Persian Gulf and the Middle East was the one that definitively separated the Mediterranean Sea from the Indian Ocean, converting the Mediterranean from an arm of the Tethys into a closed sea. The biological history of the Mediterranean after the Tethys closure is also fascinating. When the Tethys closed and the Mediterranean was isolated from the Indo-Pacific between 6 and 5 million years ago, the populations of organisms living in that sea were trapped, without possibility of genetic exchange with their Indo-Pacific relatives. That isolation produced, over millions of years, the speciation of many groups. The Mediterranean populations evolved independently from their Indo-Pacific relatives, diverging gradually in genetics, morphology, and behavior until becoming distinct species. The comparison between the closure of the Tethys and current processes of climate change is inevitable for geologists studying that period. The mechanisms that closed the Mediterranean 6 million years ago are the same tectonic mechanisms still operating today, but to them is now added the anthropogenic climate change altering evaporation and precipitation patterns in the Mediterranean basin. The current Mediterranean is already experiencing salinity increases in some of its most enclosed parts as a result of climate change, a process that on geological timescales could contribute to the next evaporation crisis when the Strait of Gibraltar closes. The result of all those successive closures, occurring in different parts of the Tethys over tens of millions of years, was that the great tropical ocean was reduced to a series of increasingly isolated basins surrounded by land. The current Mediterranean is the largest of those basins. The Black Sea and the Caspian Sea are smaller basins that became completely surrounded by continental land when tectonic movements closed their connections with the Mediterranean. The Mediterranean that we know today is the direct heir of the Tethys, but its more recent history has a particularly dramatic chapter that deserves attention: the Messinian salinity crisis, the moment when the Mediterranean dried up. The Messinian salinity crisis also provides a window into what can happen when a large ocean basin becomes isolated from the global ocean system. The isolated Mediterranean evaporated because the evaporation rate in that arid subtropical region exceeded the freshwater input from rivers and rain. That same imbalance exists in many smaller water bodies around the world today, including the Aral Sea and various inland lakes in arid regions. The Aral Sea, which has largely dried up as a result of Soviet-era irrigation projects diverting its feeder rivers, is a modern example of what the Mediterranean experienced during the Messinian crisis, compressed into a few decades rather than 600,000 years. The Messinian crisis also had consequences for the evolution of the large mammals that lived around the Mediterranean at the time. When the Mediterranean evaporated and land bridges formed between previously separated islands and continents, terrestrial animals were able to cross between Africa and Europe in ways that had not been possible before. That mixing of previously isolated faunas produced a burst of evolutionary change as different lineages encountered each other for the first time, with some species going extinct in the face of new competitors and others expanding their ranges dramatically. The impact of the Messinian crisis on North African terrestrial ecosystems is also an active area of research. When the Mediterranean evaporated, the climate of North Africa changed significantly, as the moderating influence of the sea was removed. Those climate changes affected the terrestrial ecosystems of North Africa, and some researchers have connected them to evolutionary changes in primate lineages that lived in North Africa at the time, changes that may have contributed to the conditions that eventually led to the origin of the human lineage in Africa. The climate of the Mediterranean region today. The classic Mediterranean climate of hot dry summers and mild wet winters is also partly a product of the Tethys history. The enclosed nature of the Mediterranean basin, which produces the temperature contrasts that drive the seasonal wind patterns, is the result of the Tethys closure. A different Tethys history would have produced a different Mediterranean basin and therefore a different Mediterranean climate, and without that climate the agricultural civilizations of the ancient Mediterranean world might not have developed as they did. The brine that accumulated in the Mediterranean during the Messinian crisis was an extraordinarily hostile environment. The salt concentration in those brine lakes was several times that of modern seawater, creating conditions that only the most salt-tolerant organisms could survive. The species that did survive the Messinian crisis in the Mediterranean, waiting in the remaining water bodies for the eventual refilling, were the founders of the post-Messinian Mediterranean fauna that was then supplemented by Atlantic species when the Gibraltar Seaway reopened. The ancient Nile canyon carved during the Messinian crisis is also relevant for understanding the modern Nile. The sediments that filled that canyon after the Mediterranean refilled are now the aquifer that provides groundwater to much of the Nile Valley region. The farmers and cities of Egypt and Sudan that depend on Nile groundwater are in effect drawing on water stored in the sediments that filled the ancient Messinian Canyon, a hydrological legacy of the crisis of 6 million years ago that continues to be economically important in the present. Approximately 6 million years ago, the tectonic movements still bringing Africa and Europe closer together closed the connection between the Mediterranean and the Atlantic. Without that connection, the Mediterranean was left isolated in a basin surrounded by arid land where water evaporation exceeds rainfall plus freshwater river input. The result was inevitable. The Mediterranean began to evaporate. It did not evaporate all at once. The process took approximately 600,000 years, from 6 million years ago to approximately 5,400,000 years ago. During that time, the Mediterranean level progressively descended, and the sea was replaced by a series of hypersaline lakes and evaporites that became increasingly concentrated as the water evaporated. The discovery of the Messinian evaporites at the bottom of the Mediterranean was itself a dramatic scientific event. When in 1970 the research vessel Glomar Challenger drilled the Mediterranean seafloor in the Deep Ocean Drilling Project, scientists expected to find normal marine sediments. Instead, they found salt and gypsum at shallow depth beneath the ocean floor, which could only mean the Mediterranean had evaporated. That discovery, initially received with skepticism by the scientific community, opened one of the most fascinating chapters in Mediterranean geology. The rivers that emptied into the ancient Mediterranean bed during the Messinian crisis had to carve canyons thousands of meters deep to reach the retreated sea level. The Nile carved in that period a canyon 4 kilometers deep from the plain level to the bottom, comparable in size to the Grand Canyon of Colorado but deeper. That ancient Nile canyon still exists today, but it is filled with marine sediments deposited when the Mediterranean refilled approximately 5,400,000 years ago. The refilling of the Mediterranean was also a dramatic event. Approximately 5,400,000 years ago, a new tectonic movement opened a connection between the Atlantic and the Mediterranean in the region of what is today the Strait of Gibraltar. Atlantic water began entering the empty Mediterranean basin, and geological estimates suggest the refilling could have occurred in a relatively short period, perhaps only tens of thousands of years, with a waterfall of unimaginable proportions flowing from the Atlantic into the Mediterranean. The salt history of the Mediterranean also has a human dimension that directly connects to Roman civilization. The salt deposits that formed during the Messinian crisis and that emerge at some points of the Mediterranean basin were exploited by the Romans as a salt source, a resource so valuable in the Roman economy that it was sometimes used to pay soldiers, giving origin to the word salary. That Roman salt was partly Messinian salt, formed 6 million years ago when the Mediterranean evaporated. The history of the Tethys is also written in petroleum. A significant part of the world's oil and gas reserves, especially those of the Middle East, the Caspian Sea, and the North Sea, formed from the organic matter accumulated in the Tethys seafloor sediments over millions of years. The geopolitical implications of the Tethys petroleum legacy extend beyond the Middle East and the Caspian. The North Sea petroleum fields, which funded the economic transformation of Norway, Britain, the Netherlands, and Denmark in the second half of the 20th century, also formed in basins that were connected to or influenced by the Tethys during the Mesozoic. The Norwegian Sovereign Wealth Fund, the largest in the world, is essentially the financial product of Tethys organisms that lived and died in the Jurassic and Cretaceous seas that covered northern Europe. The legacy of the Tethys petroleum raises profound questions about the relationship between geological time and human responsibility. The carbon that Tethys organisms removed from the atmosphere over millions of years created a stable climate system that allowed complex life, including eventually human civilization, to flourish. Returning that carbon to the atmosphere in the space of 2 centuries is undoing a geological process that took 100 times longer than the entire history of our species. That asymmetry between the geological timescale of carbon sequestration and the human timescale of carbon release is one of the most important facts about the current climate situation. The Tethys also contributed to the origin of the Alps in ways still being researched in detail. The Alps were not produced by a simple collision between Africa and Europe, but by a complex series of subduction events and microplate collisions occurring over tens of millions of years as different fragments of the Tethys were consumed. The result is a mountain range of extraordinary geological complexity, where rocks from the ancient Tethys seafloor are found alongside continental fragments in an intricate mosaic that geologists have been deciphering for more than a century. The Zagros Fold Belt of Iran, one of the most dramatic expressions of the Tethys closure in the Middle East, is also one of the most seismically active regions on Earth. The folds and thrusts that created those mountains are still active, with major earthquakes occurring regularly as the Arabian Plate continues pushing northward into Eurasia. The same geological forces that produced the petroleum reservoirs that made Iran one of the world's largest oil producers are also producing the earthquakes that periodically devastate Iranian cities. The transformation of Tethys organic matter into petroleum also involved enormous geological timescales of burial and heating. The organic-rich sediments that would become oil were first buried under hundreds of meters of younger sediment, compressing and heating them. Over tens of millions of years, that heat converted the organic compounds into liquid petroleum and gas, which then migrated upward through the rock until trapped in porous reservoir rocks capped by impermeable layers. That entire process, from organism death to trapped petroleum reservoir, typically takes between 50 and 100 million years. The economics of the energy transition away from fossil fuels is therefore also, indirectly, the economics of the Tethys legacy. The carbon that Tethys organisms captured from the atmosphere 100 to 150 million years ago was released back into the atmosphere during the industrial era in the space of 2 centuries. That carbon, which the Tethys had effectively removed from the climate system for tens of millions of years, is now driving the climate change that is the defining environmental challenge of our era. The full arc of the Tethys story, from the organisms that captured sunlight in the Mesozoic seas to the climate consequences of burning the petroleum their bodies became, is one of the most extraordinary causal chains in the history of the Earth system. The transition to renewable energy is therefore also a transition away from the Tethys legacy. Solar panels, wind turbines, and batteries do not draw on the stored energy of ancient organisms. They harvest the energy of the current sun or the current wind. In that sense, the energy transition represents a break with the deep geological past and a turn toward a different relationship between human civilization and the natural world. The process of petroleum formation requires specific conditions that the Tethys provided in abundance. The enormous biological productivity of that tropical ocean produced colossal quantities of organic matter that accumulated at the seafloor. When conditions at the bottom were anoxic, meaning when there was very little oxygen, that organic matter did not decompose completely but was preserved in the sediments. Over time, as sediments accumulated and pressure and temperature increased, that organic matter was cooked until transforming into oil and gas. Saudi Arabia, Iraq, Iran, Kuwait, the United Arab Emirates, Azerbaijan, Kazakhstan, and Russia today extract from the depths of the earth the petroleum that formed from the living beings that swam in the Tethys waters between 100 and 150 million years ago. In that sense, each time we fill a car's fuel tank, we are using the energy of the sun that reached the earth 100 million years ago, was captured by Tethys organisms, stored in their bodies, buried at the ocean floor, cooked by the earth's heat for tens of millions of years, and finally extracted by the petroleum industries of the present. The production of petroleum in the Middle East is also changing as countries in the region diversify their economies to prepare for the depletion of the Tethys fossil resources. Saudi Arabia, the United Arab Emirates, and other countries are investing in renewable energies and other industries with an urgency reflecting the awareness that the Tethys gift has an expiration date. Ironically, some of those solar energy investments are harnessing the same tropical sun that illuminated the Tethys 150 million years ago and whose rays were stored in the bodies of the organisms that produced the oil. The petroleum search in the ancient Tethys basins has also produced unexpected discoveries of scientific interest. In some wells in the Persian Gulf and the Caspian Sea, geologists have found microfossils of organisms that lived in the Tethys that are not known from any other deposit. Those unique fossils, recovered from depths of several kilometers in the subsoil during petroleum exploration operations, are expanding our knowledge of Tethys biodiversity in ways that conventional paleontological research could not produce. The natural gas of the Caspian Sea, which today is one of the main objects of geopolitical competition between Russia, Iran, Azerbaijan, Kazakhstan, and Turkmenistan, is also a Tethys legacy. The disputes over Caspian exploitation rights, which since the end of the Soviet Union in 1991 have involved complex negotiations between the 5 coastal countries, are ultimately disputes over the remains of an ocean that existed before the countries surrounding it existed, before the continents surrounding it existed, in a world that no longer exists except in sediments and fossils and the energy reserves it left behind. The fossils of the Tethys are one of the most powerful tools geologists have for reconstructing the history of that ocean, and also one of the most astonishing sources of information about life on Earth millions of years ago. Ammonites are the most characteristic fossils of the Tethys. Those cephalopods with spiral shells, extinct relatives of modern nautiluses, octopuses, and squids, lived in the Tethys seas from the Triassic until the end of the Cretaceous 66 million years ago, when they became extinct together with the dinosaurs in the great mass extinction produced by the Chicxulub asteroid impact. During those 185 million years of existence, ammonites evolved into tens of thousands of species, with shells of such diverse forms, sizes, and ornamentations that geologists use them today as index fossils. The presence of a specific ammonite species in a rock allows dating that rock with precision of less than 1 million years, something extraordinary in the context of geological timescale. The paleontologists who work on Tethys fossils occupy a peculiar position at the intersection of deep time and the present. When a Jurassic Ichthyosaur skeleton is carefully excavated from a Swiss alpine quarry, the bones being revealed were last disturbed when they settled to the floor of the Tethys lagoon 180 million years ago. The geologist's brush is the first thing to touch those bones since the ocean covered them. That intimacy with deep time, the sense of reaching across hundreds of millions of years to encounter a creature in the moment of its death, is one of the most powerful experiences that paleontology offers. The study of Tethys fossils has also contributed to some of the most important theoretical advances in evolutionary biology. The extraordinary completeness of some Tethys fossil records, particularly those of ammonites and marine reptiles, has allowed evolutionary biologists to study evolutionary rates and patterns of morphological change in ways not possible with more fragmentary records. The ammonite record in particular, with its exceptional temporal resolution, has been used to test theoretical predictions about evolutionary rates that cannot be tested in living organisms. The Dolomites of northern Italy are one of the most spectacular geological legacies of the Tethys. Those pale tower-like peaks are made of ancient reef limestone deposited in the shallow margins of the Tethys during the Triassic period. The organisms that built those reefs were not modern corals, but sponges and other carbonate-secreting organisms that thrived in the warm, clear Triassic Tethys. Their skeletons, accumulated over millions of years, now form the dramatic walls of one of Europe's most beautiful mountain landscapes. The study of oxygen isotopes in Tethys bivalve shells has also produced detailed records of seasonal temperature variation in that ancient ocean. Because bivalves grow continuously and incorporate oxygen isotopes into their shells in a ratio that reflects the water temperature at the time of growth, the shells of ancient bivalves contain a seasonal record of Tethys temperatures encoded in their growth rings. Those records show that the Tethys had a seasonal temperature cycle, as modern oceans do, but with smaller amplitude between summer and winter because the tropical location moderated the seasonal extremes. The amateur fossil hunters who search the limestones of the Alps, the Dolomites, the Atlas Mountains, and the Himalayan foothills are also participants in the ongoing discovery of the Tethys. Many important Tethys fossil specimens were first noticed by farmers, hikers, or quarry workers before coming to the attention of professional paleontologists. Those chance encounters between modern humans and the remains of Tethys organisms are part of the long history of the relationship between people and the fossils of that ancient ocean, a history that includes the shalograms of India and the serpent stones of medieval Europe. The conservation of Tethys fossil sites is also an active concern. The same mountains that make Tethys fossils accessible to researchers also subject those fossils to rapid erosion. A beautifully preserved ammonite exposed by a rockfall today may be completely destroyed by weathering within a few decades if it is not collected and protected. The race between discovery and destruction is a constant feature of fossil site management, and the allocation of resources for systematic collection and curation of Tethys fossils is a scientific priority in all the countries where those fossils are found. The museums of natural history across Europe are also, in a certain sense, museums of the Tethys. Their collections of Jurassic and Cretaceous fossils include thousands of specimens of Ammonites, belemnites, Ichthyosaurs, and plesiosaurs extracted from rocks that were the Tethys floor. The museums of Munich, Berlin, Paris, London, Vienna, Milan, and many other European cities preserve these collections that are both scientific heritage and direct testimonies of an ocean that disappeared before any being capable of contemplating it existed. The Solnhofen site in Bavaria, Germany, which produced some of the most exquisitely preserved fossils in the history of paleontology, including the first Archaeopteryx specimens, was the bottom of a Tethys lagoon 150 million years ago. The very fine lithographic limestone that preserves those fossils in extraordinary detail formed under conditions of very low energy and very little water circulation in that Tethys lagoon, conditions that allowed organisms falling to the bottom to be preserved before being destroyed by scavengers or decomposition. The history of the discovery of Himalayan fossils also illustrates something important about the preservation of the fossil record in general. The exceptionality of extraordinary preservation sites, known as Lagerstätten in German. The vast majority of organisms that died in the Tethys were not preserved as fossils. Their remains were destroyed by scavengers, decomposition, and diagenesis before being buried in sediment. Only a small fraction, those fortunate enough to die under specific conditions of low energy and low oxygen, were preserved. The fossils we know from the Tethys are the tip of an iceberg of biological diversity that we will never know. The Tethys also left its traces in the calcareous sediments that form the limestone that is today the most common building material in southern Europe. The calcareous Alps, the limestone plateaus of western Turkey, the Dover Cliffs in England, and the limestone hills surrounding the Mediterranean are all made of the accumulated skeletons of millions of generations of marine organisms that lived in the shallow waters of the Tethys. The Tethys Ocean's influence on global climate during the Mesozoic was also considerable, and climatologists are studying that influence to better understand how ocean configuration affects climate at a global scale. The Tethys was an equatorial ocean, situated in the planet's tropical zone, and its presence between the continental masses of Eurasia to the north and Gondwana to the south had important consequences for global ocean circulation. The equatorial currents circulating from east to west in the Tethys transported heat from the Atlantic toward the Indo-Pacific in a way very different from how current currents transport heat today. That different distribution of oceanic heat affected precipitation and temperature patterns in all the continental masses surrounding the Tethys. The Himalayan rivers that carry the eroded products of the Tethys-derived mountains down to the sea are themselves remarkable geological entities. The Indus, the Ganges, the Brahmaputra, the Irrawaddy, the Salween, the Mekong, and the Yangtze all rise in or near the Himalayan Tibetan Plateau, the most elevated terrain on Earth. Together they drain a catchment area of several million square kilometers and carry an enormous fraction of the world's river sediment load to the oceans. The deltas they build at their mouths, including the Ganges-Brahmaputra Delta in Bangladesh, the most densely populated delta in the world, are among the largest concentrations of human population on Earth, all of them built on the sediments of the dying Tethys. The rivers draining the Himalaya carry an extraordinary quantity of sediment, making them among the most powerful agents of erosion on the modern Earth. The Brahmaputra carries more sediment per unit of water than almost any other river, reflecting the extreme relief of the Himalayan range it drains. That sediment eventually reaches the Bay of Bengal, building one of the largest submarine fans on Earth. The rate of sedimentation provides a direct measure of how fast the Himalaya is being eroded, which in turn constrains models of how fast the Tethys-derived mountains are being returned to the sea from which they came. The connection between the Himalayan uplift and global cooling is one of the most important hypotheses in Cenozoic paleoclimatology. The idea that the chemical weathering of Himalayan silicate rocks has drawn down enough carbon dioxide to cool the climate significantly over the last 50 million years was proposed in the 1980s and has been refined ever since. The current consensus is that Himalayan weathering has contributed to global cooling, though it is likely one of several interacting factors rather than the sole cause. The isotopic record of Himalayan erosion preserved in the ocean sediments also shows that the rate of erosion has not been constant over the last 50 million years but has accelerated and decelerated in response to climate changes and tectonic events. Periods of glaciation, when glaciers occupied the high valleys of the Himalaya, were also periods of enhanced erosion, as glacial ice is a more powerful erosional agent than water. Those glacial erosion pulses are visible in the sediment record as increases in the grain size and volume of Himalayan-derived sediment in the Bay of Bengal. The isotopic composition of the strontium dissolved in seawater has also been used as a proxy for the rate of Himalayan erosion through time. Strontium derived from the erosion of continental silicate rocks has a different isotopic ratio than strontium derived from carbonate rocks and from hydrothermal activity at the seafloor. The record of seawater strontium isotope ratios preserved in Cenozoic marine carbonates shows a progressive increase over the last 50 million years that geochemists interpret as reflecting the increasing erosion of the silicate rocks of the rising Himalaya. That geochemical signal in ancient marine carbonates is another thread connecting the Tethys closure to the present chemistry of the global ocean. The role of the Tethys in the evolution of terrestrial life is also underappreciated. The warm, stable climate that the Tethys helped maintain in the Mesozoic supported the great diversity of Mesozoic terrestrial ecosystems, including the dinosaurs that dominated the land while the Tethys reptiles dominated the seas. The cooling and drying of the continental interiors that followed the Tethys closure contributed to the environmental changes that drove mammalian evolution in the Cenozoic, eventually producing the conditions in which the human lineage could emerge in Africa approximately 6 million years ago, precisely the time when the Tethys was experiencing its final crisis in the form of the Messinian evaporation. The role of the Himalaya in the global carbon cycle is also significant and the subject of active research. The Himalayan limestone rocks, which are the Tethys sediments lifted by the continental collision, erode as rivers descend the mountain slopes. That erosion releases calcium that rivers carry to the sea, where it is used by marine organisms to build their calcareous skeletons. When those skeletons are deposited at the seafloor, the carbon they contained is buried and removed from the atmosphere for millions of years. Geologists have calculated that the Himalayan uplift and the consequent erosion of its limestones has removed enough carbon dioxide from the atmosphere over the last 50 million years to contribute significantly to the global cooling of the Cenozoic, the period that led from the warm Eocene climates to the cooler and drier climates of the Pleistocene. The debate about whether the Asian monsoon intensified or weakened as a result of the Himalayan uplift is one of the most active in Cenozoic paleoclimatology. Resolving that apparent contradiction is important not only for its scientific interest, but also because models of how the monsoon responded to Himalayan uplift in the past are relevant for predicting how the monsoon will respond to global warming in the future. The earthquakes that periodically shake Turkey, Iran, and Pakistan are also expressions of the same process that closed the Tethys. The Arabian Plate continues pushing against Eurasia in the Turkey region, producing the Anatolian Fault that caused the devastating earthquakes of 1999 and 2023. And the Indian Plate continues pushing against Asia, producing the earthquakes affecting Nepal, Pakistan, and the Himalayan region. Those earthquakes, causing incalculable human suffering in the present, are the current sound of the Tethys closure that began millions of years ago and has not yet finished. That connection between the Himalaya, the erosion of the Tethys limestones, and global climate is one of the most dramatic examples of how plate tectonics and climate are deeply interconnected. The death of the Tethys not only transformed the geography of Asia, it also transformed the global climate in ways that affected the evolution of all organisms on the planet during the last 50 million years. The history of the Tethys is also the history of the birth of the Mediterranean as we know it today, and that history has chapters involving not only geology but also biology, oceanography, and human history. The current Mediterranean is not simply a surviving fragment of the Tethys. It is a basin that has undergone profound transformations since the original Tethys was closed by continental movements. The marine fauna of the current Mediterranean, with its fish, octopuses, sea urchins, and corals, is the result of millions of years of evolution in an environment that went from being a tropical sea connected to all the oceans of the world to being an almost closed sea with limited connections to the Atlantic and no direct connection to the Indo-Pacific. The legacy of the Tethys in human culture extends well beyond the Shaligrams of India. The ancient Greeks and Romans, who lived on the shores of the Mediterranean, were fascinated by the marine fossils they found in the limestone rocks of their mountains. Herodotus and Strabo commented on the presence of shells in desert rocks far from the sea, attributing them to ancient floods or to the former extent of the sea. That intuition, that the presence of marine fossils in inland rocks was evidence of former sea coverage, was correct, even if their understanding of the mechanism was incomplete. The Roman relationship with the Mediterranean was at a deeper level a relationship with the Tethys. Roman ships were built from timber felled on limestone hills formed from Tethys sediments. Roman legions marched on roads paved with the same limestone. The aqueducts that brought water to Roman cities were built from lime mortar produced by burning Tethys limestone. The material culture of Roman civilization was, to a remarkable degree, assembled from the resources of the Tethys that the Mediterranean preserved for them. The future of the Mediterranean under current climate projections is deeply uncertain. The warming of Mediterranean waters, the acidification from increased carbon dioxide absorption, and changes in circulation patterns are already affecting the marine organisms of that basin. Tropical species from the Atlantic and Red Sea are extending their ranges into the warming Mediterranean. Cold water species are retreating to even deeper refuges. The biological future of the Mediterranean is being written in real time, and it has no precedent in the 5 million years of the post-Messinian Mediterranean. The dugongs of the Indo-Pacific and the manatees of the Atlantic are living proof of the Tethys biogeographical legacy. Those two groups of marine mammals, which share a common ancestor that lived in the Tethys, were separated when the ocean closed and their populations were divided between the surviving Indo-Pacific and Atlantic basins. Over the last 20 million years, those separated populations evolved into distinct families, the dugongids of the Indo-Pacific and the trichechids of the Atlantic. Reading that evolutionary divergence backward in time leads directly to the Tethys as the shared homeland of both groups. The ancient Greek word for the sea goddess Tethys was used by the Austrian geologist Eduard Suess in 1893 when he named the ancient ocean he had inferred from the distribution of marine fossils across Europe and Asia. Suess, who was also the first to propose the concept of Gondwana as a former southern supercontinent, saw in the distribution of Mesozoic marine rocks across what is now mountainous inland territory the evidence of a vast ancient sea. His naming of that sea after the Greek goddess of the ocean was both scientifically apt and culturally resonant. The role of the Mediterranean as the cradle of Western civilization is also inseparable from its geological identity as a Tethys remnant. The enclosed nature of the Mediterranean, which made it navigable with the relatively simple vessels of antiquity, was the product of the Tethys closure. The rich fisheries that provided protein to Mediterranean civilizations from the Bronze Age onward were the biological legacy of the organisms that colonized the Mediterranean after the Messinian refilling. And the limestone and marble that Mediterranean civilizations used to build their temples, palaces, and aqueducts were Tethys seafloor sediments. The Roman Empire, in that sense, was built on the bones of Tethys organisms. The future of the Mediterranean under climate change is also shaped by its Tethys legacy. The Mediterranean is one of the regions of the world most severely affected by warming, with temperatures increasing approximately 1.5 times faster than the global average. The marine organisms of the Mediterranean, which evolved in the specific conditions of that basin since the Messinian refilling, are now facing conditions that have no equivalent in the last 5 million years of Mediterranean history. The rate of change is faster than evolution can track, making the biological future of the Mediterranean highly uncertain. The cetaceans, whales, and dolphins also have an origin story connected to the Tethys. The terrestrial ancestors of cetaceans, the Pangea, lived on the shores of the Tethys approximately 55 million years ago in what is today Pakistan. Those animals, wolf-like in general morphology but with increasing adaptations to aquatic life, were gradually colonizing the Tethys during the following millions of years, evolving toward increasingly sea-adapted forms until producing the whales and dolphins that today dominate the oceans. The Tethys was, in that sense, the evolutionary cradle of cetaceans. The Posidonia meadows of the Mediterranean, those marine plants that form highly productive ecosystems in the shallow Mediterranean waters and that are today endangered by climate change and pollution, are also Tethys heirs. Posidonia oceanica, the dominant species in Mediterranean meadows, is a relict of the marine plants that lived in the shallow waters of the Tethys and became trapped in the Mediterranean when that sea closed. They are plants whose lineage goes back to the Tethys that have survived the Messinian crisis, the refilling of the Mediterranean, and tens of millions of years of oceanographic changes. The Lessepian migration through the Suez Canal, opened in 1869, is in that context an involuntary evolutionary experiment of enormous scientific interest. For the first time in millions of years, marine organisms from the Indo-Pacific have access to the Mediterranean, and the results of that access are being studied by marine biologists worldwide. More than 100 species from the Red Sea have established populations in the Mediterranean since 1869, competing with native species and in some cases displacing them. That biological invasion is in a certain way a partial reopening of a connection that the Tethys closure had severed millions of years ago. The Tethys also left its mark on the religious traditions of the people living near its remnants. The Shaligrams of India, the sacred Ammonite fossils venerated in Hindu tradition as manifestations of Vishnu, are among the most unexpected links between the geological history of the Tethys and the spiritual history of one of the world's oldest civilizations. That veneration of Tethys cephalopod fossils is one of the most extraordinary connections between the geological history of an extinct ocean and the human world that emerged millions of years after it disappeared. There is something philosophically remarkable about the history of the Tethys that goes beyond geology and paleontology, the scale of time in which it operated and what that scale of time tells us about the permanence of things. The Tethys existed for approximately 200 million years. Modern humans, Homo sapiens, have been on Earth for approximately 300,000 years. If we compare the history of the Tethys with the history of humanity, the ocean lived for a period 600 times longer than the time we have existed as a species. The story of the Tethys also invites reflection on the human relationship with geological time, and with the difficulty of grasping timescales that exceed anything in human experience. There is something in the history of the Tethys that is directly calming when contemplated at the end of a day. The ocean existed for 200 million years. It was filled with extraordinary life. It died, slowly and irreversibly, and from its death came mountains and seas and the material wealth that sustains modern civilization. Nothing about that process was tragic in the cosmic sense. It was simply the Earth doing what the Earth does, rearranging its surface in response to the forces of its interior. That perspective does not diminish the importance of what we experience. It simply places it in a context so large that it becomes, paradoxically, easier to bear. The Tethys also reminds us that the Earth is not finished. The planet is not a fixed backdrop for the drama of life, but an active participant, continuously reshaping the stage. The continents that closed the Tethys are still moving. New rifts are opening in East Africa that may in tens of millions of years produce a new ocean. The Mediterranean is closing. The Atlantic is widening. The Earth is a work in progress, and the Tethys is one of the most complete chapters we have of that ongoing work. The history of the Tethys also connects to the history of human spiritual traditions in ways beyond the shalograms. The ancient Greeks, living on the shores of the Mediterranean Tethys remnant, developed their own mythological explanations for the marine fossils they found in mountainous inland regions. Tethys herself was a Titan goddess of the sea in Greek mythology, the personification of the productive ocean that fed and connected the ancient world. That the name of a geological ocean should echo the name of a mythological deity, both representing the vast productive sea from which civilization drew its sustenance, is one of the more poetic connections between deep time and human culture. 200 million years is a number that can be spoken in a second, but cannot be genuinely imagined. The mind grasps it conceptually but cannot feel it the way it feels the difference between a minute and an hour. The best we can do is to compare it with other things we find large. The age of the oldest human civilization is 5,000 years. The age of the dinosaurs is about 200 million years. The age of the Tethys is about the same. Those comparisons help, but they still do not convey the felt reality of time on that scale. What the geological record does convey, more powerfully than any number, is the sheer quantity of change that 200 million years of Earth history contains. The Tethys opened, flourished, was transformed by the evolution of new organisms, suffered mass extinctions that killed most of its inhabitants, recovered, and was finally closed and converted into mountains, all within those 200 million years. That is not the history of a static background setting for evolutionary events. It is itself a drama of transformation on the grandest scale. The geological perspective on time also has a practical implication for how we think about environmental change. The rate of change that characterizes the current geological epoch, driven by human activities, is extraordinarily fast by geological standards. The temperature changes we are producing in decades took thousands of years during natural climate transitions of the past. The species extinctions we are causing in a century would normally take tens of thousands of years during mass extinction events. The geological record of the Tethys, which shows us what happens when the rate of environmental change exceeds the adaptive capacity of life, is directly relevant to understanding the risks of the current situation. And yet, the Tethys no longer exists. It was destroyed by geological forces operating at speeds imperceptible from the timescale of a human life, at rhythms of centimeters per year, but that were unstoppable on the timescale of millions of years. The mountains growing where the Tethys was continue growing today. The Mediterranean that inherited its waters continues reducing its connection with the Atlantic as Africa continues pushing northward. In some tens of millions of years, the Mediterranean will have disappeared too, replaced by another mountain range that the collision between Africa and Europe will have produced. The Ammonites of the Tethys also tell us something about the nature of evolutionary success and its vulnerability. Those organisms had evolved for 180 million years to be perfectly adapted to the conditions of the Tethys seas. That perfect adaptation was also their fragility. When conditions changed catastrophically with the Chicxulub impact, they had nowhere to go evolutionarily. The less specialized survivors, the sharks, the teleost fish, the scleractinian corals, rebuilt the marine world in the millions of years that followed. Today those survivors' descendants fill the oceans with a diversity that in some respects surpasses that of the Tethys at its height. The history of the Tethys is, in that sense, also a story of resilience, of the capacity of life to survive the most extreme transformations of the physical environment in which it exists, and to reinvent itself in the new conditions those transformations create. The ocean can disappear. The mountains it becomes can erode back to the sea over tens of millions of years. And through all of that transformation, life finds its way, adapts, and continues. That perspective, of an ocean 200 million years in history that ends up being converted into mountains, has something that calms when contemplated from the scale of a human life. The problems that seem permanent are also, on the geological timescale, temporary. The landscapes that seem eternal are also, on that scale, ephemeral. Oceans are born, they live for tens or hundreds of millions of years, and they die. And in their sediments, in their fossils, in the mountains that grow where they stood, they leave a record of what they were that the geologists and paleontologists of the present can read if they know how. Modern research on the Tethys is combining data from multiple disciplines in ways that produce an increasingly detailed and more surprising picture of that lost ocean. The carbon stored in the soils and sediments of the ancient Tethys is also a legacy that is only now being quantified. The Tethys was an extraordinarily productive tropical ocean, and the organic carbon that accumulated in its sediments over 200 million years was eventually transformed into the petroleum that powers much of the modern world. But not all of that carbon became oil. Some remained in the sedimentary rocks as dispersed organic matter, and quantifying how much carbon the Tethys captured and stored during its lifetime has implications for understanding the global carbon cycle of the Mesozoic. The ongoing research into Tethys paleoclimate is also providing important calibration data for the climate models that predict future warming. The warm climates of the Mesozoic, when the Tethys existed at its maximum extent, provide natural experiments for understanding how the Earth responds to high greenhouse gas concentrations. Atmospheric CO2 during the Cretaceous was 3 to 5 times higher than pre-industrial levels, and the global temperatures were correspondingly warmer. Reproducing those past climates in climate models provides a test of those models that is independent of the historical instrumental record, strengthening confidence in the models that pass the test. What the Tethys ultimately offers us is not just knowledge but perspective. The perspective of an ocean that outlived the dinosaurs, that was present when the first mammals were small nocturnal creatures hiding from predators in the Jurassic undergrowth, that witnessed the rise and fall of dozens of dominant groups of organisms before any of the groups that populate the modern world existed. From that perspective, the urgency of the current moment does not diminish but changes character. It becomes the urgency of responsibility, the responsibility of the only species that has ever understood the story of the Tethys to act in ways consistent with that understanding. The Tethys is also a reminder that science is a form of time travel. When a paleontologist reads the fossil record of the Tethys, they are in a real sense visiting a world that existed long before human civilization. That ability to reconstruct the deep past from its traces in the present, unique among all the phenomena we know in the universe, is one of the most remarkable capacities of the human mind. The Tethys existed. We know it existed. We know how it lived and how it died. That knowledge is one of the great achievements of scientific inquiry. Tonight, as sleep comes, the Tethys is still here in the world around us. In the Mediterranean waves below the moonlight. In the gasoline in a parked car. In the marble of a cathedral. In the Ammonite fossil on a museum shelf. In the earthquake tremors under the mountains of Iran and Nepal. In the monsoon rains falling on the Indian plains. The Tethys died 200 million years ago and is still shaping every day of our lives. That is the nature of deep time. Nothing is ever truly gone. It only becomes something else. The research into Tethys history will continue producing new discoveries for generations of scientists to come. New drilling campaigns into the sediments of the Mediterranean, Black Sea, and Caspian will reveal more details of the Tethys closure. New fossil finds in the mountains of China, Pakistan, and the Middle East will add to the picture of life in the Tethys. And new analytical techniques will extract more information from the rocks and fossils that have already been collected. The story of the Tethys is not finished. We are still learning to read it. The high-latitude climates of the Cretaceous, when the Tethys was still a major tropical ocean, were also dramatically different from today. Fossil evidence of forests in the Arctic and Antarctica during the Cretaceous, combined with the absence of polar ice caps, tells us that a world with very high CO2 is a world without polar ice, with much higher sea levels, and with dramatically different ocean circulation patterns. The current trajectory of CO2 increase, if continued, is pointing the climate system in a direction that has not existed since the Tethys was at its height, with consequences for sea level and ocean circulation that will unfold over centuries and millennia even if emissions stop tomorrow. The Tethys, therefore, tells us something important not just about the past, but about the future. It tells us that the Earth system is capable of states very different from the one that supported human civilization. It tells us that those different states can be entered through the accumulation of greenhouse gases in the atmosphere. And it tells us that once entered, they can persist for tens of millions of years. That is not a comfortable message. But it is an honest one, drawn from the most complete record of deep time that we have. The record written in the rocks where the Tethys once lay, in the fossils of the organisms that lived and died in its waters, and in the mountains that grew where those waters once flowed. The future of Tethys research also promises substantial discoveries. The deep subsurface geology of the Middle East and Central Asia, which preserves the record of the Tethys in its sedimentary sequences, is still incompletely explored. New drilling programs, new seismic surveys, and new analytical techniques are continually revealing aspects of the Tethys history that were unknown just years ago. The pace of discovery in Tethys paleontology and paleogeography has been accelerating in recent decades as research programs in China, India, and other countries with access to critical Tethyan rocks have intensified. The geochemistry of oxygen isotopes in Tethys fossil carbonates allows reconstructing the ocean water temperatures at different moments in its history. Those reconstructions show the Tethys was generally warmer than current oceans, with surface water temperatures of between 20 and 30 degrees Celsius through most of its history. But they also show significant variations related to the great climatic events of the Mesozoic, including several periods of extreme warming known as oceanic anoxic events, in which water temperature increased several degrees and the oxygen content of the bottom water fell to almost zero. Those oceanic anoxic events of the Tethys are also responsible for some of the largest accumulations of organic matter known in the geological record, and therefore for some of the most important petroleum reserves in the world. The future research on the Tethys also has the capacity to change our understanding of events we thought we understood well. New geochemical data, new radiometric dates, and new computational models are continuously refining the chronology of the Tethys closure and the consequences of that closure for global climate. In the last 20 years, the date for the start of the India-Eurasia collision has been revised several times as new data has appeared, and the debate about the exact date and speed of the final Tethys closure remains active. That dynamic of continuous revision is not a sign of weakness in science but of its strength. The ability to revise earlier conclusions when new evidence appears is the most valuable characteristic of the scientific method. Tonight we have explored the history of the Tethys from its birth in the fragmentation of Pangea to its death beneath the colliding continents, through the extraordinary life it harbored for 200 million years, the resources it left buried in its sediments, and the mountains and seas that exist today where the Tethys once stood. What emerges from that exploration is an image of the Earth as a planet on which nothing is permanent on the geological timescale. Oceans are born and die. Mountains grow where there was sea, and the sea covers where there were mountains. Continents move, collide, fragment, and reunite again in configurations that have no precedent in human history but that the geological record documents with astonishing clarity. The fossils of shells at the summit of Everest are the most powerful symbol of all of that. They are there not as the result of any cataclysm, not as the product of any accident, but simply as the logical consequence of 200 million years of continental movement and 55 million years of collision between India and Eurasia. They are shells that lived at the bottom of a tropical sea and that today are at the highest point of the terrestrial surface, and that journey of 15 kilometers from ocean depth to the summit of the world, accomplished over tens of millions of years, is perhaps the most extraordinary story that any object on Earth has lived. The next time someone looks at the Mediterranean coastline, the Alps or the Pyrenees, or the next time they use gasoline produced in the Middle East, Or the next time they see a photograph of the snow-covered Himalayan summits, they will be looking at the remains of the Tethys, an ocean no one has seen, that disappeared before the first primate climbed its first tree, that disappeared before human beings existed, but whose remains are everywhere. In the rock, in the petroleum, in the mountains, in the seas that inherited its waters, and in the fossils of the animals that lived in it and that the earth has kept patiently for millions of years for us to find. The Tethys gave us the petroleum that built the modern world. It gave us the mountains that shape half the continents. It gave us the Mediterranean that cradled Western civilization. And it gave us the deepest lesson that geology teaches, that what seems permanent is only temporary, and what seems lost is only transformed. Tonight, as sleep arrives, the Mediterranean continues existing where the Tethys existed before. Its waters are the heirs of an ocean that knew Ichthyosaurs and Ammonites, that witnessed the birth and death of ecosystems with no equivalent in the modern world, and that died slowly beneath the weight of the continents that collided to create the highest mountains on Earth. The waves that strike the coasts of Italy, Greece, Spain, and Turkey are the heirs of the waves that struck those same coasts millions of years ago, when the sea bathing them was much larger and much more ancient. And the mountains rising above those coasts continue growing, millimeter by millimeter, pushed by the same forces that closed the Tethys and that have not finished their work. The story of the Tethys is not a story with an ending. It is a story with a transformation. The ocean became mountains. The mountains are becoming sediment. The sediment will return to the sea. And somewhere in that vast recycling of material through geological time, the atoms that were once in the shells of a Tethys ammonite are now in the air we breathe, in the water we drink, in the ground we walk on. Nothing is lost. Everything becomes something else. That is the deepest lesson of the Tethys, and it is one of the most calming thoughts the natural world offers to anyone willing to hold it in mind. The next time you fill a car with gasoline produced in the Gulf, or stand before a marble column in a Mediterranean city, or watch the monsoon rains fall over India on the news, you will be seeing the Tethys. 200 million years of history, compressed into the ordinary details of a single day. That is what deep time does. It makes the ordinary extraordinary for anyone willing to look. If this journey kept you company tonight, subscribe to the channel. There are many more worlds waiting to be explored in the dark. The Earth has many more stories to tell.